Good afternoon. Yes, good afternoon. You're welcome. Thank you very much I want to thank you, all the organizers of this, for having Federal Highways here to present this research. We're very excited to disseminate this. I am pretty lucky because I kind of inherited part of this project because it was already ongoing before I started. So what I want to do is we'll first start out with, this is a very interesting photo. It's kind of comedic. This is part of the pooled fund that I'll talk about. And you have all these engineers sitting around looking at the pavement and all looking down. You ask 20 engineers, you get 20 different opinions. And I was coming on the plane, and I saw that, and I said, well, that's pretty good. I want to include that. I'll start with acknowledging the co-authors for this paper. First, Shisheng Ki. He is our support staff there. He manages the AL facilities. It's very good knowledge. Arun Shenoy, he's also a rheologist. Dr. Ghazi Al-Khatib, also a research engineer. Terry Arnold, he's our chemist. Jack Uchev, he is our current team leader for the materials and construction team, and previously that was Tom Harmon. Also want to include here John D'Angelo. John D'Angelo, Tom, and Jack were very active in getting this research started with this pooled fund. I'll want to give you an outline first. And so I'll basically discuss the objectives, construction, instrumentation, and go on to the testing. But I think what I really need to do and really send out some thanks right now is the industry partners for getting this research started, and specifically Texpar, who helped out with the terminal blend, Consul Pave, that's George Sousa, for the Arizona wet process, Rubber Pavements Association, also MacTech. They were involved in some of the mix design for the gap-graded mixture that I'll include. If I could keep going on, there's a lot of industry support in this, and I want to definitely take this time and say thank you. For example, this is the crumb rubber blender that was diverted to the project. It was temporarily diverted. I think it was on its way to Europe, I believe. I'm learning some of the history as I go. And they dropped it off. They took it there to Virginia, where our research site was, and we were able to get use of that. So it's an excellent example of industry stakeholder support. Very, very excited about that. Also want to call out our pooled fund participants. It's about 18 different states altogether, a pooled fund, and also a state planning and research, one which focused on rubbers, the other one focused on polymer modification, and now those both are joined together. So a little bit of background about this project. It's intent to refine SuperPave. In '93, the Federal Highway Administration had an ALF project which basically verified the SuperPave spec. In '99, we knew that there were some issues with polymer modified binders capturing the performance, so an NCHRP study started with 9007 looking at a wide variety of binders, which was kind of a scoping study to determine what binders we're going to place under the ALF next, which is where we get to this 2001 experiment, which was constructed in 2002. We nicknamed another study, was a spin-off study, 6780, and I'll get involved in that. So we wanted to expand the number of binders we were looking at there. So the research objectives in this is to look at construction. We had some non-destructive tests we were looking at, rutting and fatigue cracking, both in the lab and also in the ALF, and low temperature cracking as well. So primarily, we're trying to refine the SuperPave spec to account for modified binders. Secondarily, we're looking at mechanistic empirical design, looking at crumb rubber mixtures and the sample performance test. For those of you who aren't familiar with the accelerated load facilities machines we have, these are the Australian design, and we have two on site. I'll talk about the binders which were selected. Essentially what we've got is a control, an unmodified control, an air-blown binder, one with an ethylene terpolymer, linear grafted SBS polymer. One which has it's SBS, but it's a very low modulus, but also has a high polymer content. That's also nicknamed 64-40. We're looking at definitely the Arizona wet process, also the terminal blended crumb rubber, and also a control mix with fiber. All of these binders the target was to bring them up to the same PG. That way, if they have ideally the same PG, they should all ideally perform the same. And that's not the case, as we can see here. And that will give us excellent ground truth, which we'll base new binder specifications from. So what you can see here, in lane 1, we have a composite section. This is a 4-inch section. It's Arizona crumb rubber by the wet process. It's a gap-graded mix, 2 inches on top of 2 inches of the control mix. 4 inches of the control, an air-blown binder, the other modified binders, the crumb rubber terminal blend. We have our fiber binders. Then we switch into a 6 layers where we have, instead of 4 inches of asphalt, now we have 6 inches of asphalt. And we have, not the same, but we have a few of the core binders we're looking at there. What we are using to load these pavements is a 425 super single, and that's also a product of some research done at Turner Fairbank. This was found to be the most damaging tire, so a lot of accelerated load facilities use this tire. It provides about 40% more damage than standard duals. In each test lane, we have an opportunity for 4 tests. In the lower sections, we do fatigue at 2 temperatures. And in the upper section, we have rutting. We are targeting at 64 Celsius. We've completed at 64 Celsius, which leaves an open lane for sometimes a shakedown test, but sometimes rutting at either a much higher temperature for some special purposes, but also we've done some rutting at lower temperatures so we can provide some additional data for NCHRP 930A, which is new rutting models for the Mechanistic Empirical Design Guide. I'm going to breeze through these instrumentation here. We can, if you want to ask questions, we can talk about that later. But we're essentially using, we have a LTP weather station. We're looking at moisture, temperature. We're looking at rutting only in the asphalt layer and also strain gauges. We have a layout here, and for each center of the wheel path, we've got 2 transverse and 3 longitudinal strain gauges. The current status right now is we've completed all 64, rutting at 64 Celsius. Majority of the 19 Celsius fatigue is done. That takes a long time. We plan to have, by the end of next year, the rutting at the 28 degrees Celsius sections next. Those take a bit longer. So getting into the meat, this is what we see for the 4-inch sections. This is rutting observed only in the asphalt layer. This is rutting that is observed in the 6-inch layer. What I tend to look at rutting with this type of graph. So this is 90% confidence intervals. We have 8 points along the wheel path, and actually we have some variability in field rutting. Even in well-controlled APT facility construction, you can have variability in rutting. And we see that here. So what we see here is for the thinner sections, there's some kind of a pecking order in terms of rutting. But this is some statistical techniques to do clustered ranking. So this is what we see here. The terminal blend performing the best in the Arizona crumb rubber section next there. In the thicker lanes, it's a different story. But you know what? They're basically very similar rutting. And I think, personally, in terms of the goals of the experiment, they're very similar running from very similar PGs. So we'll get to the PG spec later. In terms of fatigue cracking, this is where we see really big differences between the performance of these materials. Rutting, not so much, but fatigue cracking, definitely yes. This is a visual observation of the rutting. Our ALF technicians do strain, they map the cracks. They do crack mapping. They do, at regular intervals, they go out and they do various rankings that I'll talk about next. But what I wanted to do here was kind of pause and look at the cracking I'll go back, and if you look at lane 1, we don't see any surface cracking. This is the composite section with crumb rubber Arizona over the control, okay? What we see is that there actually was cracking. We've taken some cores, and the cracking started at the bottom of the control mix, went through the 2 inches, reached the boundary at the Arizona wet process, and basically arrested. And we are in the process of looking at initiation and propagation of these cracks with portable seismic pavement analyzer and other techniques, because when we do crack mapping, as you can see here, we're only looking at what arrives at the surface. Okay, but what we see here, this is if you look at percentage of the cracked area versus number of ALF passes. This is the composite section with the Arizona wet process. Up to 300,000 passes, we're not seeing any surface cracking. Here, to give you a reference, this is the terminal blend section. In between, we have the terpolymer, the SBS with the control and the airborne performing worse as expected. A different kind of flavor of looking at fatigue cracking, cumulative crack length, and you see the same story here. What you notice, now we have the fiber mix in here, okay? So that one is also performing quite well too. There's different ways you can do the ranking. You can look at the number of cumulative crack length at a certain number of cycles, or vice versa, and we'll talk about that here. So, and it tells the same story, whichever way you look at it. Passes the surface crack initiation, that's when we see it on the surface. This is the ranking we see here. Passes to a 50-meter crack length, that's what we see there. And it's the same ranking here. And then crack length at 100,000 passes. The Arizona mix is off the scale. There's no cracking to measure, but we can see the terminal blend is right in here. I apologize for that color, and it's middle of the pack. Laboratory tests, we are looking at a wide variety. French pavement rut tester, the Hamburg wheel tracker, SuperPave shear tester, 2 of the simple performance tests. Actually, I think now it's being called the SuperPave performance test. Don't quote me on that. Indirect tension testing, the overlay tester from TTI. There's a paper at TRB on that, and I won't get into that. We can probably talk about that during questions. Bending, beam, fatigue, I've got a couple stars there for a reason. And then direct tension, push and pull. I'll share some of the ranking that we've seen for high temperature for rutting here. What we see is a clear ranking here, and the French rut tester, which is basically a large pneumatic wheel in a confined box. We see a similar type of ranking with we see a clustered ranking that we kind of saw under the ALF. And this will also be correlated to the rutting under the ALF as well. Repeated shear at constant height, that's the SuperPave shear tester. Before we started getting involved with the simple performance tester, this kind of gave some good ranking. We can either look at repeated shear or the modulus. What I do want to share with you is the results from the simple performance tester. Like I said, SuperPave performance tester. If some of you aren't familiar with that, this is one of the not a prototype. This is in production. This is offered by an Australian company. We have this in our laboratory. It's a streamlined, user-friendly method to do these advanced characterization tests, dynamic modulus, and also repeated load permanent deformation that Dr. Kalush has much experience with. When we look at the number of cycles to 2% strain in the repeated load test, and we compare that to rut depth, it depends on how you interpret that. Okay, and if you look at straight crude numbers of R squared, it's going to tell you one story. I don't think we should be using this type of correlation for such small data points. I think when you look at the trends of these, you actually see you see a trend, and I think that's a better story. Now, these were unconfined tests, and we're currently performing some tests under confinement, and I'll mention very briefly, this is an analysis where we're looking at the multi-axial stresses under a wheel, which determine which location is rutting under the ALF being mostly disturbed. What's the hot spot? What's the most disturbance? And then tailoring a repeated load test, confined repeated load test to those conditions. That's ongoing right now, but if you look at the results from unconfined, repeated load testing, it's very good. And at this point, I want to stop and I want to talk about what I mentioned in the beginning. the 6780 binders. And what we've done is, instead of using these 7 binders, which are all focused, clustered around one PG spec, what we've done is we've gotten a whole bunch more binders and have a wider range of PG. So that's how it got the nickname 6780. So what we're doing, the idea here is you identify a surrogate test that gets you that correlates to field performance best. And then what we can do is then, instead of building more ALF lanes with these 6780 binders, we use our lab surrogate tests to do these correlations on a much wider range of mixes and more data points. It's much more statistically healthy that way. That's ongoing, and the simple performance tester will be a good focus of that, the repeated load permanent deformation test. Push-pull fatigue. Let me pause here and say something. We got a new loading and data acquisition system at the Turner Fairbanks Center, and we busted it. We started doing some bending beam tests, and we broke it. It's being repaired, and while it was being repaired, we had the opportunity to look at some of these other fatigue tests that are going on. And what I'll also back up and say right now, Dr. Seuss has really been pushing for me to get him some mixes. I'm going to get off my rear end and actually share some of those mixes with him, because he has a very good way of looking at these mixes, specifically the chrome rubber mixes and bending beams. So I definitely am going to commit to sharing those materials with you. In the meantime, we're going to be looking at this axial push-pull test here. And this has some benefits, and it also has some disadvantages that I'll admit to as well. Number one, it comes from the superpave gyratory compactor, so the aggregate orientation is different. But again, we're looking at this in terms of a surrogate test, okay? Also, the stress state is axial. It's not bending like in the beam fatigue, so we're able to look at some of these continuum damage theories, which give us maybe a more mechanistic, laboratory mechanistic definition of failure. If you look at what we use as a 50% reduction in modulus, I don't know how realistic that is. If you look at some of these mixes that we've started looking at, you can get quite a lot of reduction in modulus, but they're still performing before you get to a crack, a macro crack. I'll also mention that we're able to look at healing in these tests. And I think that healing is really important when we start looking at modified binders, but especially Arizona wet process, because when you have, the binder contents are much larger in these mixes. So when you have much more binder, you have much more opportunity for healing. And we can really start to look at how these materials behave. So what you're seeing here, this is a healing process after a day. And you almost get complete regain in the strength. Forgive me, this is the dynamic modulus in the push-pull test versus number of these load cycles. That's pretty dramatic, and I think it's really important, and that's something that we don't want to overlook in this laboratory characterization. So I'll get to some of the tests that have been completed. This is in terms of lab mix to ALF rutting. As I said, the French rut tester has about a mediocre correlation. This is R squared. The SST did pretty good, depending on whether you were looking at thin section, 4 inches versus 6 inch. The flow number also had a different correlation, but I want to bring in the science here and warn you about this. This is a small number of points, and it's very sensitive to the number of the points we're looking at, and also because this suspect alveoli mixture was removed. There were some issues with introducing the lime for anti-stripping into that, and I can get to that in the question section if we want to. For fatigue characterization, IDT tensile strength provided a fairly good correlation, but we need to expand to more mixes. The dissipated creep strain energy, this is Ray Roquet's method from Florida. That is in the completion stage, and that's also could be a good simple performance test for cracking. It's very simple to do indirect tension. Dynamic modulus provided somewhat of actually a pretty good correlation, but again, it depended on what thickness you were looking at. I'll also pause here for a second and say a lot of the details are in the paper, and I suggest you can go there. But I wanted to highlight what's going on. The TTI overlay tester, Fuji Zhou and Tom Scullion are working with that. And they got extremely good correlations there. And that's also maybe an opportunity for a simple performance test for fatigue cracking. In terms of binder parameters correlating to the ALF for rutting, we've looked at a number. And we've used the SuperPave binder ETG to vet these binder characteristics. Low to moderate correlations are obtained, but the leaders in terms of this are this high temperature spec that was based from Arun Shenoy, our rheologist. It's a modification of the spec, but you're also looking at different stiffness. It's probably the easiest to be implemented, while John D'Angelo, this is his passion, he's looking at this multiple stress creep and recovery. That is also coming to fruition soon. For fatigue correlations, again, low to moderate on these various parameters looked at. However, we got some good correlation with this one modified parameter that Arun worked on. Again, it's very simple to implement, and a different flavor from Hussein Bahia at University of Wisconsin. That's looking a little bit closer. It's a little more substantial, but it can provide some more information. So, in summary, we have a lot of ongoing efforts with this laboratory and ALF characterization. I want to say that this study is providing a lot of good, what Tom Harmon calls ground truth to the performance of these mixtures. We could not have done it without state and industry support. We're very, very thankful for getting this project off the ground. The pooled fund project is probably going to be closed out, and a meeting is expected in early 2007. The rubber modified pavements are performing very well in rutting and fatigue when you look at these other modified mixtures. With that, I'll ask for questions, or if you have some arrows you want to shoot at me, I'll take those as well. And I also put my email address there for other questions.